installment of something that only Berkeley can do, which is present talks by people who won 7 Turing Awards for work they did at Berkeley. Probably our most famous is Dick Karp. Dick Karp is kind of the pathbreaker, the first Berkeley faculty member to get a Turing Award. Besides the Turing Award, he's won the National Medal of Science, and we heard about in the interview today that his dad, who was a teacher, kind of inspired him to leave the cushy IBM Yorktown Heights and went to get back into teaching, because he loved teaching so much. And in fact, not only did he win the Turing Award, National Science, he won Berkeley's highest honor, the Distinguished Teaching Award. I'm delighted. He was a role model to those of us who were here many years ago. Great researcher, tremendous teacher, department chair, and a really humble, really nice guy. And that's the model that we all try and follow. With that, Dick Karp.
Thank you. Thank you very much, Dave. You've done us a great service here at Berkeley by putting this series together. And you're a wonderful interviewer. You actually do your homework and come up with relevant questions. Thank you. So let me start by reading the opening words of the 1972 paper, Reducibility Among Combinatorial Problems, which is the main support for my Turing Award. All the known general algorithms for and by the way, there are typos which I will correct, so. All the known general algorithms for computing the chromatic number of a graph, solving an integer programming problem, or computing the optimal tour of a traveling salesman encounter a combinatorial explosion in their worst case execution time as the problem size grows. We will show that these problems and many others are equivalent, and here's where the typos begin, in the sense that if combinatorial explosions are inevitable for any one of them, then they are inevitable for all the problems in the class. Oops. So I'll return to the theme of that paragraph. But before I do that, I want to go back in my own personal history, which in the field began in the late 50s, and talk about some of the nice algorithmic work that was done there and also some anomalies that came up. So we'll be talking here about polynomial-time sequential deterministic algorithms. So no parallel algorithms in this talk, no distributed algorithms. And we'll say that an algorithm runs in polynomial time if its worst case, if there is a constant c such that its worst case execution time is big O of n to the power c for some constant c, where n is a measure of the size of the problem instance, and the claim has to be true for all instances. Now, there are a couple of possible objections to this formulation. The first has to do with the value of this parameter c, which is typically an integer, sometimes irrational. So if c is 1 or 2 or 3, it's plausible to say that a polynomial time algorithm with that running time is efficient. But if c is much larger, then n to the 5th, n to the 6th, n to the 7th, then it becomes dubious to say that the algorithm would be a practical one. But for convenience in classifying problems, theoreticians have tended to ignore this issue and sweep all of the polynomial time algorithms into the same bucket. The other issue is with the constant hidden by the big O. And the constant of proportionality in front of the n to the c. And clearly, if that constant is enormous, then the problem, the algorithm really isn't of much use because its running time will not be reasonable until the size becomes very large. But we tend to overlook this, and in many cases, we sort of get the right sentiment from this way of viewing it, that we get low-degree polynomial algorithms. The constants tend to be not too extreme, and the algorithms are useful. So while I was growing up in the 60s and 70s, a number of important and efficient polynomial time algorithms were created. Minimum spanning tree. By the way, I'm going to assume that you know basic graph theoretic language. So does anybody object if I talk about spanning trees without defining them, or paths, or flows, or cycles?
You can lead.
Okay.
Just ask a question.
Just ask a question. Do you all know what a matching is in a graph? Beresford does. Okay, that's good enough. Now, there's some interesting anomalies, and a famous one is the simplex algorithm for linear programming. Linear programming, as most of you will know, is the problem of minimizing linear function of n variables subject to linear inequality constraints. And in a historic piece of work that's had much influence over the decades, George Dantzig introduced the simplex algorithm. I'll talk about it later, but the important thing to notice about it is that it's not a polynomial time algorithm, even though it's widely used in the world of computation and very reliable. But there are pathological examples that take exponential time on rare instances. And for that reason, we don't classify the simplex algorithm as a polynomial time algorithm, because the definition of polynomial time refers to the worst case instances of the problem. The next paragraph sort of drives home the point about comparing algorithms by their asymptotic running times. This can be misleading. And one prominent example is the problem of multiplying two n by n matrices. If you just write down the obvious straight line program that the formula suggests, you'll get an n-cubed algorithm. Strassen created a sensation sometime in the 60s by giving an algorithm that ran in time n to the power log to the base 2 of 7. That's a smaller exponent than 3. And had reasonable running time. The constants involved in the running time formula were not too bad. The algorithms with the best asymptotic running times have a running time proportional to n to the power 2.37, much better. But none of them are used because the constant hidden in the big O is so large that these algorithms, even though they have a smaller exponent, do not prevail over the earlier ones until n is huge. And that's one of the concerns in interpreting for users the significance of polynomial time algorithms, because you get these mathematical tour de force that create algorithms with a small exponent but an unbelievably large running constant, and they're of little use, so it becomes a mathematical exercise to create them, although perhaps justifiable as mathematics. Now I want to formalize two important classes of computational problems. So these will be decision problems. This means that the problem that on any instance, the algorithm will yield, will classify the instance as either yes or no. And the instances are the strings over some alphabet. So a decision problem can be described as a partition of the set of strings over some alphabet into the accepted strings and the rejected strings. And we denote by P the class of decision problems solvable in polynomial time. And the motivation to study this class was first developed by Cobham in terms of the mathematics of the classification, and later Edmonds argued for the emphasis on polynomial time algorithms as the yardstick for computational efficiency. A little more subtle is the class of problems NP. These are the problems for which an accepted string can be verified in polynomial time given a witness. A witness is just a string such that there is some algorithm which, given that string and given a problem instance, will determine if it's the case that that input is accepted. So, for example, sometimes the witness is very obvious. For example, if we take the problem of coloring a graph with 3 colors, it's believed tentatively not to be in P for reasons that I'll describe a little later. But it does lie in NP, and the witness is simply the coloring itself. Because once the graph has been decorated with colors, it's easy to verify that no 2 vertices of the same color are present. So problems of that character, where an input can be verified rapidly in polynomial time, even though it can't necessarily be computed in the absence of that witness, those problems characterize the class NP, which stands for non-deterministic polynomial. So some examples of problems that are in NP but are not known to be in P are graph coloring, maximum independent set, maximum clique, Traveling-Salesman Problem in a decision version, and integer solution of systems of linear inequalities. In all of those cases, the witness is obvious. It's just the result of the operation of coloring, or it'll be the independent set itself, or the clique itself, and so forth. But none of these problems are known to be in the class P. And the biggest open question in this area is whether P equals NP. It seems intuitively that since finding a solution is, in our experience, much harder than verifying a solution once found. Think of a Sudoku puzzle, for example. It may be hard to solve, but once the solution is laid bare, one can check it readily. It seems rather implausible that the classes P and NP could be the same, but this is not ruled out in our present state of knowledge. A particular problem in the class NP is the satisfiability problem of propositional calculus. In this problem, a set of expressions called clauses are given. Excuse my typography. I'm using plus for the inclusive or because my keyboard didn't have the usual symbol for it. And I'll use prime for complementation for a similar reason. So here we have a list of clauses. The first one is A or not B. The second one is B or C, etc. And this set of clauses will be said to be satisfiable if one can assign truth values to the variables such that every clause is true. So for the upper example, if we take A to be false, B to be false, and C to be true, then we'll get, that means that A prime is true and B prime is true. We'll get a true literal in every clause, and that's the criterion for the conjunction of those clauses to be satisfiable. One can check that if we look at the second example, then there is no solution. There is no truth assignment to the variables, which makes all the clauses true. And the satisfiability problem is the decision problem of whether a collection of clauses is can be made simultaneously true. And Steve Cook's famous theorem from 1971 is that the classes P and NP are equal if and only if the satisfiability problem lies in P. Steve Cook, by the way, was an assistant professor at Berkeley. He's a magnificent scientist, and we spent much of the discussion session this morning lamenting the fact that Steve left Berkeley 45 years ago. We've never gotten over it. So now we'll say that a decision problem is NP complete if P equals NP follows from that problem being NP. So when I say that the satisfiability problem is NP complete, that means that if there is a polynomial time algorithm for the satisfiability problem, then P equals NP, and in fact, and so every problem in NP is solvable in polynomial time. And Cook proved that the satisfiability problem is NP complete by a clever argument involving a Turing machine representation of a generic problem in NP. So in some sense, the satisfiability problem is as hard as any problem in NP, because if you could solve it in polynomial time, if it lay in P, then the same would be true of all the problems in NP. Another way to look at this NP completeness is that a problem is NP complete if it's written in a language or a format that is sufficiently flexible and informative that you can encode any problem in NP. So the NP complete problems are the hardest problems in NP, and either all of them or none of them lie in P. Now, Cook opened the way to studying NP complete problems by showing that the satisfiability problem is NP complete. But once he had that initial discovery, we have a fairly straightforward methodology for proving that many other problems are NP complete. So we'll say that problem X, satisfiability for example, is polynomial time reducible to problem Y if and only if there is a polynomial time computable function that maps accepted strings of X to accepted strings of Y and rejected strings of X to rejected strings of Y. In other words, the reduction from problem X to problem Y transforms instances of X into corresponding instances of Y that have the same status accepted or rejected. And it follows that if a polynomial, if an NP-complete problem is X is reducible to a problem Y in NP, then Y is also NP-complete. Because if you could solve if X is NP-complete and mapping it to Y, you can solve the corresponding instance of Y, then via that reduction, you have a way of solving any NP-complete problem by going first to X and then mapping it to Y. So Y becomes NP-complete. And so what, in effect, Cook proved, although he used a different definition of the reducibility than I used in my work, is that every decision problem in NP is reducible to SAT. And the way to think about this is that the language in which SAT is defined, Boolean algebra, is rich enough to express every decision problem in NP. And in general, if problem X is reducible to Y and X is NP-complete, then Y is also NP-complete. And this gives us a mechanism for drawing many problems into the NP-complete class. And what I did in 1972, having seen Cook's result that SAT is the most general problem in NP, I had the intuition that these complete problems are hard. They're not solvable in polynomial time. And many familiar problems that occur in practice are also going to have the same universality or generality. They're also going to be NP-complete. And here are the 21 examples. These are all frequently formulated problems in commerce, engineering, and so forth. And one shows that all of them are NP-complete by simply constructing chains of reduction, starting with SAT, the original NP-complete problem, and showing that, and using the transitivity of the reducibility relation to show that SAT is reducible to every one of these problems, and hence they're all as hard as any problem in NP. So either none or all of these problems lie in P. Most of us believe that none of them lie in P, but because we've never found a polynomial time algorithm for any of them, but it remains an open question. And by now, many thousands of problems have been shown to be NP-complete. And the reduction techniques are so streamlined and easy that one really can't get a paper published with a new NP-completeness result because they've turned out, they are in most cases pretty routine. And so we still want to understand whether these problems are in P, and if they are not, how can we cope with them? It's widely believed in complexity circles that no sequential algorithm for satisfiability has sub-exponential worst-case complexity. The running time has to be, it's believed that every algorithm in its worst case will have running time at least c to the n for some c greater than 1. Nevertheless, instances of the satisfiability problem continue to arise in digital design, in program verification, and various other industrial applications. And SAT solvers, programs that solve industrial strength instances with millions of variables, are found to be often successful. So there's something, sorry, let's see. Oh, sorry. Give me a second here. Okay. So here we have this apparent paradox that theoreticians consider SAT a hard problem because it's not expected to have a polynomial time algorithm. And yet, for the instances that occur in these applications, the empirical discovery is that SAT solvers are extremely successful in most cases. The solvers, there are various types of SAT solvers with different heuristics in their makeup, but they are all based on the following inference rule called resolution. From A or X and A prime or Y, infer X or Y. So here A is a variable, A prime its complement, and X and Y are subclauses, or and in fact arbitrary Boolean expressions. And we can see that this is true because since A and A prime can't simultaneously be true, it's either the case where that A is false, in which any satisfying solution to the given clauses, A or X and A prime or Y, can only be satisfied if X is true to make the clause A or X true. Or if A is false, then similarly Y has to be true. Therefore, in any solution in which those two clauses are satisfied, the clause X or Y must also be satisfied. And this one inference rule is the principal one used in these SAT solvers. Just a minute. Here we are. So here I've shown a resolution proof that the 6 clauses at the top of the page, that set of clauses is not satisfiable. And the way we're going to prove it is to perform successive resolution steps to derive new clauses until we finally derive an empty clause that has no literals in it, and therefore nothing can be made true, and the clause is false, and therefore, since the clause has been inferred, we know that the whole system of clauses is not satisfiable. So basically, the algorithms operate through chains of resolution steps, although in the background, there is a lot of processing going on to determine which resolution step to perform next. Now, we can also talk about approximation algorithms. These will be polynomial time algorithms, but their purpose will be to not to, and the approximation algorithms arise not in decision problems where the answer is yes or no, but in problems where there is some value or some function is being computed. So for example, if we wanted to compute the one such problem would be to find the chromatic number of a system of clauses, and the polynomial time approximation algorithm would not be required to get the actual chromatic number, but could get something close. So a maximization problem is defined as a decision problem to determine which strings are relevant, which strings are accepted, together with a value for each accepted string. So for one example would be the maximum clique problem. A clique in a graph, you probably all know, is a collection of mutually adjacent vertices, a complete subgraph. And the max clique problem is the problem of finding a clique in a graph with a maximum number of vertices. So I should have drawn a little diagram here where we have a big graph with a couple of hundred nodes and many edges, and you're supposed to find the clique of size 5, and after you realize that you can't do it, we give you a witness for the clique of size 5 just by highlighting 5 vertices, after which you can directly observe that they're mutually connected. So the clique problem is an NP, and as a decision problem, but as an optimization problem, the value of the clique is the size, the number of vertices it contains. And an approximation algorithm is said to achieve approximation ratio R of n, some function of the input size, if on every input of length n it produces an accepted solution whose value is at least R of n times the cost of an optimal accepted input. So in the max clique problem, you might be achieving an approximation ratio of 1/2. That would mean that on every graph, your polynomial time optimization algorithm would return a clique at least half the size of the maximum clique. And this is required to take place for every possible input. And this is one of the objections to approximation algorithms, because if there's just one input anywhere for which the approximation ratio is not achieved, then the algorithm is not considered a good approximation algorithm from this point of view. Whereas in many practical situations, one would be happy with an algorithm that usually delivers a good solution. But the theoretical complexity class property that's typically considers is to require all of the inputs to produce.
Water here.
Thank you. To produce at least a certain fraction R of n of the optimal solution. And one of the deepest areas of complexity theory is the area of hardness of approximation, which shows that, whose aim is to show that certain approximations are not achievable in worst case by polynomial time algorithms. So one famous result is that one cannot estimate one cannot guarantee unless NP equals NP, no approximation ratio of the form n to the minus epsilon can be achieved for the max clique problem. So for example, it says that if P is NP, then you cannot have an approximation algorithm that returns a clique whose size is at least 1 over root n of the size of the maximum clique. This result follows from a famous theorem called the PCP theorem, which I'm not going to discuss because no less than 5 eminent experts on the PCP theorem were sitting out in the hall as I walked into the room. And I don't have that level of expertise. But this at least gives me an opportunity to boast that contributors to hardness of approximation, many of the important contributors to hardness of approximation either were trained at Berkeley. So Shafi Goldwasser was involved in the first paper on hardness of approximation in, I think it was 1996. And the PCP theorem, which I'm leaving undiscussed, was developed when they were students by Sanjeev Arora and Madhu Sudan, students of Umesh Vazirani, and by Rajiv Madhwani. So there are many important contributors to this very important area of hardness of approximation. In the next section of the talk, I would like to turn to algorithm construction. And one of the discoveries, one of the developments in the last few years is the importance of algorithmic techniques from linear algebra to solve computational problems. Various problems involving finding flows in networks, for example, have traditionally been solved by actual combinatorial constructions, which actually create, by a series of augmentation, maximum flows through a network. But it's been discovered in the last few years that one can also attack these problems very successfully by linear algebra, improved methods for finding eigenvalues and eigenvectors, computing maximum flows and minimum cuts, solving systems of linear inequalities and equations, and convex optimization. And I want to dwell a little bit on linear programming. Linear programming is the problem of maximizing or minimizing a linear function of n variables subject to linear inequality constraints. Many economic problems can be formulated as linear programming problems. There's a geometric interpretation of the linear programming problem. The feasible region for a system of linear inequalities, think of it in 2 dimensions, for example, as a bunch of planes which enclose together some polyhedron. And in general, in n dimensions, the set of feasible solutions to the linear inequalities is a polyhedron in n dimensions. And the maximization problem, say, is to find the furthest point in a given direction on a convex polyhedron described by linear inequalities. So you have some box-like structure with many facets, a diamond, if you will, and you want to compute the highest point on the diamond. So the geometric interpretation of the problem is to find the furthest point in a given direction on a convex polyhedron described by linear inequalities. The simplex algorithm of Danzig is extremely simple. It first has an initial phase where it obtains some vertex, some corner point of the polyhedron. And then it just slides along the edges of the polyhedron, always moving in the direction that it's seeking to move toward the optimum. And extensive experience with the simplex algorithm shows that in practice it's highly efficient and still widely used, but it was not a polynomial time algorithm because of some pathological examples. And starting around 1984 with the work of Karp, attention turned to interior point methods where the computation follows a discrete path through the interior of the polyhedron, trying to move in the direction of increasing the objective function, but also taking into account the necessity of avoiding the boundary of the polyhedron. So you have some sort of force which rewards the path for moving toward the optimum, but punishes it from getting too close to the boundary. And the first polynomial time interior point method was due to Karp while he was finishing up his PhD at Berkeley. I've learned from Dave to put in a plug for Berkeley whenever possible. And there have been extensive improvements in the original interior point method, with the best method known currently due to two fellows who were at the Simons Institute at Berkeley. There's another plug, which show how to reduce the number of steps, the number of iterations where you move from one point to another, to a successor along the path through the interior, and also their method reduces the time to create, to compute the direction for the next step. So the world champion algorithm for linear programming is probably due to Lee and Sidford, but the simplex method is still a contender, even though it's not polynomial time. Now, a related problem is the integer programming problem. This is a much harder problem. It's NP hard. That's the counterpart for optimization problems of NP-complete. So again, integer programming seeks to find the furthest point in a given direction. And here I have another typo. Find the furthest point in a given direction on a convex polyhedron described by linear inequalities and the requirement that all variables are integers. So if you want to think about the geometry of this problem, you have the linear inequalities which define a polyhedron, and then within the polyhedron you have a lattice of integer points, which are the feasible solutions, because the requirement for feasibility is to satisfy the inequalities with integers. And what is commonly done is to begin by solving the linear programming relaxation, where you relax the requirement that the variables are fractional, and then repeatedly add further linear inequalities that exclude the current optimal solution but preserve all integer solutions. So for example, if you started by solving the linear programming relaxation, you would wander along the boundary of the polyhedron defined by the linear inequalities until you get to a highest point or a maximum point. And then if that point had fractional coordinates, you would cut away part of the polyhedron to get rid of that extreme point, but not get rid of any integer solutions. And so the integer programming algorithms all have that characteristic of slicing away at a polyhedron, starting with the linear programming relaxation, and then inferring inequalities that do not lose any integer points, but do get rid of the current extreme point. There are great packages for integer programming. Exactly what lies in those software packages is in the realm of industrial secrets. And they do perform rather well, but the integer programming problem is a much harder one, and they don't always succeed in running rapidly. A maxim that I learned from my friend Dan Gusfield, who's just written a book on integer programming in computational biology, is always try integer programming, it may work. Sort of just the opposite of the usual point of view of complexity theory. But it does work in many cases. For example, if you want to solve the Sudoku puzzles in the newspaper, you can easily figure out how to write the Sudoku puzzle as an integer program. And any of the current solvers will knock off those Sudoku puzzles very rapidly. But there are no guarantees for these integer programming packages, and you may be disappointed. Now, I want to combine together some of these elements of linear programming and integer programming in connection with the so-called traveling-salesman problem, which I think most of you are familiar with. Here you have n cities, or if you will, vertices, and you have a travel cost from any city to any other city. So the data for the problem would be a complete graph on n vertices, and then for every edge of the complete graph, a number giving the travel cost from going from one city to another. And typically, usually one assumes the symmetric traveling salesman problem, which means that the distance of going from I to j is the same as the distance of going from j to I. And one further assumes the triangle inequality, that going directly from I to k is cheaper or no more expensive than going from I to j and then from j to k. So given this matrix of distances satisfying these two properties, which make it a metric, we want to find a tour of minimum total distance through cities 1 through n. You want to find the optimal order, in other words, of visiting the cities by sliding along sliding along edges and returning to the starting point. So the tour is just a single cycle through all of the cities. The problem is NP-hard, the analog of NP-complete for optimization problems. But Applegate, Bixby, Fatal, and Cook, not the same Cook, have honed their methods for using LP followed by cutting planes, as I described, to get the exact solutions of enormous instances up to 80,000 cities. To do 80,000 cities, they had to run many computers for many months, but it was a single run. And for more moderate-sized problems like 1,000 cities, these methods are really usable in practice, but not always successful. There's a very cute approximation algorithm for the traveling salesman problem. It achieves a ratio of 3/2. I'll try to describe it so rapidly and yet understandably. It depends on the notion of an Eulerian graph. You may remember the earliest theorem in graph theory is that if you have a connected graph in which every vertex has even degree, an even number of neighbors, then it's possible to create a cycle through which traverses every edge exactly once. So the idea of the Christofides approximation is to construct a suitable graph connected and with even degrees that passes through all of the vertices of the which has a circuit passing through all of its vertices, we will argue that a particular construction achieves an approximation ratio of 3/2, at most 50% worse than the optimal solution. So to construct our Eulerian graph, we want it to be connected, and we want it to have all degrees even. So first we want to economically construct a connected graph through all the cities. Well, that's just the minimum spanning tree. You all know that there's a slick, greedy algorithm for solving the minimum spanning tree. So we'll construct such a tree, but it's not yet an Eulerian graph because it doesn't have even degrees. It's known to have an even number of vertices of odd degree. And so what we do is match up the vertices of odd degree with a minimum weight matching. And now what we will have constructed is an Eulerian graph passing through all the cities. So once again, because I went through that quickly, you start with a minimum spanning tree. Then to get an Eulerian graph, you match up in pairs at minimum cost all of the odd degree vertices of the structure. And that'll give you a connected graph that covers all of the vertices and has even degrees. So we're guaranteed that we can traverse that graph covering every edge exactly once and returning to the starting point. Now you almost have a traveling salesman tour, but the only difficulty is that you can visit a city several times, which we usually don't allow in the solution. But because of the triangle inequality, we can remove the repeated occurrences of a city. So if you have a city that occurs more than once, you take one of its occurrences and replace its two incident edges in the Eulerian graph by a single edge bypassing the middle vertex. And so what you finally end with is the traveling salesman tour. Now, it's easy to see that the total cost of the tour is less than the cost of the optimal traveling salesman problem. Pardon me, the total cost of the tree is less than the cost of the traveling salesman problem. And a small argument, which I won't go through, allows us to say that the cost of the matching of the odd degree vertices has at most half the cost of the optimum tour. So we are now guaranteed that this construction gives a tour of at most 3/2 the cost of the optimal tour. So how good is that? Well, examples are known where the tour constructed by the Christofides method actually costs 4/3 the cost of the optimal tour. But it's not known that that's the worst case. So the worst case is at least 4/3 and at most 3/2. And it remains an open question exactly what the best approximation ratio is. But it's a nifty, clever algorithm and also useful. Now I want to talk about how we can tackle the linear program, tackle the traveling salesman problem as a linear program. So we're going to relax the integer programming formulation. So I haven't stated the integer programming formulation, so here it comes. Given the graph of the traveling salesman problem, we will assign a 0 or a 1 to every edge because we want an integer solution. A 1 would indicate the traversal of that edge. A 0 would indicate its omission. And the sum of the weights of the edges incident with each vertex is 2. That's because a tour is required to go through an edge once, and then therefore there'll be 2 incident edges, one entering and one leaving. And now the structure has to be connected. So if you have any proper subset of all of the vertices, there has to be some connection to the outside. And because it's a tour, if you leave that set, you also get back to it. And so there must be at least 2 edges with exactly 1 endpoint in the set S. And all of those conditions can be expressed as linear integer inequalities, or equalities. So what we have there is an integer programming problem. And the way we're going to tackle it is by relaxing the integer programming problem to a linear programming problem. So the linear programming relaxation simply removes the integrality requirement. So now you can have a fractional weight, say 0.4 on some edge, and it's difficult to put an interpretation on that because in the end we have to get to obtain integral weights. But the motivation for using the relaxation is that we're later going to use, after we've solved the relaxation, we'll use the cutting plane method to get an integer solution. So now, having introduced fractional variables, we have a linear program. It's a huge linear program because it has an edge, typically n-squared edges, and even worse, an exponential number of constraints, because we have a constraint for every proper subset of the set of vertices. But even though it has exponentially many constraints, it turns out that it's of a type that can be solved in polynomial time. Here I'll sweep the reasoning for that under the rug and simply say that you can solve the LP relaxation. And once you've got an optimal solution to the LP relaxation, you can start applying cutting planes to hack away at the polyhedron and eventually get an integer polyhedron. There is a little more to it than that, but that's the key concept behind the algorithms. And as I say, the world champion solutions so far have been for examples with more than 80,000 cities and many months on many computers. But the method is very successful on moderate-sized problems as well. Now, for a long time, we didn't have anything analogous to the 3/2 approximation that we got for the symmetric traveling salesman. And now we want to look at the asymmetric traveling salesman problem, where the triangle inequality holds, but the distance from I to j may be different from the distance from j to I. And this asymmetry is reasonable in many applications are where you're configuring some objects and moving from configuration I to configuration J may not have the same cost as moving in the opposite direction. So this is the asymmetric traveling salesman problem, but we still require the triangle inequality. So getting back to the symmetric traveling salesman, the Christofides algorithm achieves an approximation ratio of 3/2 and 4/3 is conjectured. And unfortunately, the algorithm by Svensson et al. Just derived recently for the asymmetric traveling salesman problem is a triumph mathematically because for the first time it achieves a constant approximation ratio. But it's one of those mathematical curiosities that you wouldn't use because the constant in front of the big O is in the thousands. So it's an interesting construction, but more from the mathematical elegance point of view than from practice. One of the authors of this work actually suspects that the correct approximation ratio would be 2, which would be wonderful, but that's not backed up by anything except intuition. Now, let's see. We've gone over an hour. I have some more material. What should I do, Dave? Should I go on a bit, or?
5 more minutes?
5 more minutes. Okay, then what? So what I'll do is skip one-dimensional bin packing. Another linear programming-based process. And I'll talk very briefly about 3 pieces of work, but not really going into details, but just dwelling on the human relations that developed in connection with these 3 pieces of work. So this will be just more anecdotal and not very demanding mathematically. So the matching problem on graphs is the following. You've got a graph with weights on the edges, and you want to construct a maximum weight matching. Yeah, okay. No, I'm sorry, I'll take that back. A maximum matching of minimum weight. And for the special case of bipartite graphs is where the vertices are in 2 classes, and each vertex connects to vertices of those 2 classes. So we can think of the vertices as boys and girls, and you want to match up the boys with the girls at minimum cost. Long ago in the 70s, John Hopcroft and I gave an algorithm for bipartite matching, the case of the boys and the girls, in which the running time was very low. It was the number of edges times the square root of the number of vertices. But for a long time, there was resistance. There was an inability to achieve that same time bound for the non-bipartite matching, where there's no gender requirement. When Silvio Micali and Vijay Vazirani were students in my combinatorial algorithms class, they heard about this non-bipartite matching problem and decided that they felt that the time bound for the bipartite case should also be achievable for this one. And in fact, somebody had claimed it, but with a mistaken result, mistaken algorithm. So they became fascinated with this problem Unfortunately, they had the requirement to pass my combinatorial algorithms course. And being good researchers, they ignored all the assignments in the course, handed in no papers, no final, no nothing, but seemed to be on the verge of solving this problem. So the question is, what grade do I give them? Well, the lowest grade I could give them without getting them in trouble with the authorities at Berkeley was a B-. They didn't deserve a B- because they hadn't solved the problem, but I gave it to them anyway. And when they did solve it, I retroactively gave VJ an A. Silvio didn't care less by that time. The Rabin-Karp string searching algorithm. This is a fingerprinting algorithm for finding a particular pattern in the string. Again, I'll avoid any technicalities. It's basically a linear time algorithm that marches along the string and in a clever way uses a prime number fingerprint to flag the occurrences of a particular pattern. Anyway, I heard about this problem from Michael Rabin, who is one of my all-time role models and one of the great people in our field. And Michael came to lunch and gave a construction for solving this problem in linear time. But it was a little cumbersome. And I was sitting there and listening to Michael, and I had an inspiration. I said to him, Michael, you don't need the matrices. There's an easier way to do it. And he had to agree, and so he made me a co-author. He even wrote the paper. So now I have a paper with Rabin for a rather minimal contribution. The third example is with Mike Sipser. When Mike was a graduate student, he was mostly doing complexity theory. But he wanted a little application, a little example of in programming. And so we decided to study a very primitive algorithm for finding a maximum matching in a graph. It's such a stupid algorithm that I hesitate to show it to you, but here's what it is. You start with the graph, and you want to get a maximum matching means a maximum number of edges no two meet at a common vertex, a maximum number of disjoint edges. So if you think about it, if the graph has a vertex of degree 1, you lose no generality by matching it to its unique neighbor. That can't be a bad move. So the Karp-Sipser matching algorithm, I blush to admit, is match up vertices of degree 1 and delete them as long as possible. And when you don't have any vertices remaining of degree 1, pick any edge and put it in the matching and continue. So Mike programmed this up, and we noticed empirically that there's a threshold occurring in the behavior of this algorithm on random graphs. If the average, it appeared from our empirical work that if the average degree is less than something like 2.7, then the whole graph will get eaten up by these moves connected with degree 1 vertices, and therefore you'll get an optimal solution. On the other hand, if it's above something like 2.7, then you would expect that this phase where you're making optimal moves would not eat up the whole graph, and there would be some loss, some suboptimality. So that we eventually wrote down, we described the process by a system of differential equations going to the continuous limit of a discrete particle system where the particles are the vertices. And we could solve the system of differential equations, and that revealed that the threshold is the number E, 2.718. But our limiting process on the system of differential equations was intuitive but not rigorous, and we started sifting through the literature to find sufficient conditions for the correctness of what we were doing, even though we were using a continuous limit instead of the actual discrete system. And we never succeeded in clinching it, but we were so pleased with the way E popped up that we published a little paper anyway. And we continued to think about it using some methodology by a mathematician named, I'm losing it. Who's the main character in Heart of Darkness? What's his name? Has anybody read Heart of Darkness? Kurtz, that's right, Kurtz. So there was this paper by Kurtz which gave sufficient conditions for the limiting process to be valid. And we were never able to make the conditions of Kurtz's theorem apply exactly right. And so after we gave up and just published our incomplete result, Mike sent me for my copy, for my birthday, a copy of Heart of Darkness by Kurtz, with Kurtz as the main character. So with that, I know I've bounced around a lot, but I've just been trying to show you some of the developments that tickle me, and I hope you found them interesting.
Time for a couple of questions. Just need a first one. Oh, wow.
Could you say a few words about the status of information-based complexity theory in the bigger world of complexity theory?
I'm not an expert on information-based complexity, but I find that one of its assumptions is that you can compare two real numbers to determine which is the larger. And it seems to me that I don't see a concrete way of doing that. As long as their decimal expansions continue to agree, how do you complete the comparison? And so for that reason, I think it's an interesting mathematical theory, but I have a little concern about its applicability. And I said that in the preface to their book. They asked me to write a preface, assuming that I would write a complimentary one. And I raised this point. Maybe I made too much of a deal about it, but we're still on speaking grounds.
Next question?
Yeah, Bill?
Traveling-Salesman Problem. You assume the triangle inequality.
Yeah.
There have been times when it costs more to fly non-stop from one city to another than it would cost to pause at an intermediate city. For example, if you wanted to get from Seattle to Los Angeles, it could cost you more at one time than if you stopped in San Francisco.
Yeah, you can deal with this in your model. You just take the distance from city A to B to be the shortest travel distance, even with intermediate stops, and make that the element in your matrix. And then you're fine, except that what you end up is a tour with repeated cities, but you have no, if you don't object to that, then it's a perfectly fine way to proceed. So you can accommodate it.
Other question?
Yeah.
Do you know of any connection between the P equal NP problem and problems in mathematical logic?
Connection PNTP and mathematical logic. I don't have a microphone. That didn't work.
There is a characterization of NP by Fagan, which gives a logical formalism for membership in NP rather than a computational model. But that's as much as I know about the connection with logic, unless you count Boolean algebra as logic.
you were talking about NP-completeness and the reduction of one algorithm to another through that. Does the fact that like an algorithm X or a problem X reduces to a problem Y have any bearing on designing a algorithm to solve that problem, or is that relationship just restrained to the issue of asymptotic behavior?
It just relates to the expressibility. So, for example, the Max-Clique problem, the satisfiability problem can be seen as a special case of the Max-Clique problem. And so if you have a system of clauses for the satisfiability problem, there's an automatic way of writing a corresponding system of cliques, an input to the Max-Clique problem. And so if you could solve the Max-Clique problem, then you can map backwards and solve the SAT problem. So this has nothing to do with how you compute in terms of the difficulty of solving the problems. It just relates to the ability to map one to the other.
Okay, how about this last question?
Are there complexity classes suitable to discussing these notions of somehow average time complexity, or of this approximate, how well it is to approximate things?
Right. Yeah, this is a serious lack in our methodology. So in the early 70s, I spent some time working on average case for instances drawn from the space of random graphs. So there's this Erdős-Rényi model of random graphs where you have a number of vertices and a number of edges, and the edges are just thrown in randomly. So that's a nice class of graphs. We can say a lot of things about it, and I and others were able to show that you can compute Hamiltonian circuits and all kinds of interesting things for these random graphs. But even though it was fun, it was resisted by the community because they saw no reason to believe that the Erdős-Rényi model had anything to do with typical graphs in applications. So after a while, even though I was having a lot of fun with it, I gave it up. There is some theory by Leonid Levin about average case complexity, which does allow you to make analyses which allow a larger collection of a more general notion of random graph. I'm not too familiar with it. It doesn't seem to have become a very active field. So that's all. This is a huge lack in the field, that practitioners really only care about what happens on typical instances, or at least they're not worried about an occasional pathological situation, such as you get in the case of the simplex algorithm. Nobody really worries about the fact that these bad examples exist for the simplex algorithm. And yet, complexity theory has no way of offering its approval to those situations. So it's a big deal, a big issue, and I'm afraid that I don't have an idea at the moment how to tackle it.
I get to do the last question, which is the question that I've been ever since Ostrad said this. Why Berkeley? Why would we have 7 projects, Turing Award projects, as opposed to our competitors who seem equally talented? You've been here from the beginning. You have any insights about this?
Frankly, I don't think there is a phenomenon there. I think it's a bunch of. Did the theory group's presence here help your architecture work?
I was thinking more. Okay,
Yeah.
I would say, in asking this to Silvio, he talked about the community,
Yeah.
the rich community and the cooperation and collaboration that the theory community, and I think that's something that was there before I got here, and what it was that kind of behavior was encouraged, and whether that was one of the keys.
Yeah, that's probably true. And I haven't spent enough time at our competitors to know what it's like there. But
He has.
but it's certainly a hallmark of the place. I would agree with that.
Okay. All right, with that, let's thank Dick again. I guess they want you to sign that on the recording. I'd like you to sign that. So it seems like Silvio didn't really care very much about rules.